Hello, welcome to STAT's virtual event, a conversation with the Stat Madness crowd favorite, sponsored by Novartis. Thanks for joining us. I'm Gideon Gill, managing editor here at STAT. I'm sure many of you by now know how these Zoom panels work, but I'll just quickly go over a few housekeeping items. So at the bottom of your screen, you should see several icons. Use the chat feature to chat among yourselves and to send a message directly to the STAT team. Please do not put your questions for the chat in there. Instead, if you do have a question, and we certainly welcome your questions, we'll be trying to answer them throughout the panel. Please use the Q&A feature to type your question, and we will answer them live if we can. In the Q&A window, you should also be able to see the questions that other attendees have asked and upvote the questions you would most like to see answered. Well, as I said, we'll be taking questions throughout the chat, so please don't wait till the very end to submit them. Before we get started, I'd like to welcome Wendy Yajnik, Global Head of Academic Partnerships and External Innovation at the Novartis Institutes for Biomedical Research. She's going to provide a sponsored introduction of today's event. Please note that these sponsored remarks have been pre-recorded.
Hi, I'm Wendy Yajnik, and I oversee academic partnerships and external innovation at the Novartis Institutes for Biomedical Research. Stat Madness is, of course, a competition among academic institutions, so you may be wondering why you're hearing from someone in the industry. I'd like to answer that in two ways. First, I was once an academic myself. I studied HIV-1 in the early 90s when little was known about the underlying biology. As anyone who has ever worked on a disease as devastating as HIV knows, the science is just the starting point. The ultimate goal, of course, is to get these therapies to patients who need them. And this is what motivated me to leave the bench. I ended up spending 18 years in the technology licensing office at Brigham and Women's Hospital, where we commercialized early stage scientific ideas and partnered with biotech, pharma, and VCs to start companies. And then I moved to industry. I had heard some wild ideas when I was at the Brigham. In academia, there was a meeting with scientists who had noticed something interesting about kids who ate popsicles. They intended to have dimples. And this sounds like a very academic observation. But what happened was, based on that observation, Mass General was able to develop a fat freezing technique that inspired growth for a multi-million-dollar industry. I wonder if someday the skinny greasy mice research that took the Stat Madness Prize this year will be a basis for an equally or even more successful weight loss intervention. When I moved to Novartis, I heard of another wild idea that started in academia, but only could be translated into therapies through a partnership with industry. There was a proposal to take leukemic patients' immune cells out of the body and re-engineer them and reintroduce them into their bodies to attack cancer cells in the body. This is, of course, CAR-T, which was first marketed by Novartis through a collaboration with Penn. Since then, CAR-T has become a standard of practice for some of the most aggressive lymphomas that affect patients. The kind of partnering is now a model for so much of what we do at Novartis. We have multiple postdoctoral training programs focused on both basic science and interdisciplinary work of drug hunting. We have a global scholars program that funds academic investigators with up to $1 million for 3 years, pairing them with our scientists that have excellent drug hunting capabilities. We are also innovator agnostic at Novartis. We care about good ideas no matter where they come from, because we can help ensure that that idea gets to help patients. That's the real reason you're hearing from me, because when discoveries from academia are developed into safe and effective approved therapies, we can transform people's lives together. This is really not such a thing. There is really not such a thing as academia versus industry. There is only academia and industry, ideally working hand in hand. Thanks for the opportunity to share my thoughts with you today, and congratulations to the winning team. I hope your ideas contribute to a brighter future for all of us. Thank you.
Well, hello again, and thank you again, Wendy, for that introduction. So now I'm really excited to introduce for today's discussion Dr. Taku Kambayashi. He is Associate Professor of Pathology at the Perelman School of Medicine at the University of Pennsylvania. And he has achieved an unprecedented feat because his skinny, greasy mice that you'll hear a lot more about today won, for the first time, won both halves of the Stat Madness competition, both the popular vote in the bracket style competition, for which we had over 350,000 votes cast. And he also was selected as the winner at our stat by the attendees at our Stat Breakthrough Science Summit a few weeks ago. And so you really caught people's attention with this, Taku. And so I would like to start off maybe with you giving us the same pitch that you gave to the at the Stat Breakthrough Science Summit, because it really obviously worked.
Great. Thank you for the kind introduction, Gideon. Really happy to be here. Yeah, it was really a lot of fun to be in person at the summit. We met there. I met Gideon there at the summit, and we had a great time. So I added a few more slides than at the summit because it was only a 5-minute talk. So it's going to be a little bit less than 10 minutes for today, but I'll start. All right. Can everybody see my screen? Is it? Yep. Okay. All right. All right. So the title is Stimulating the Immune System to Sweat Out Fat. That's what we actually eventually found out. But of course, that's not how we initially started our journey. So I'm going to lead you through some of the initial steps of how we got here. So as everybody knows, obesity is a serious health problem. In the US alone, you have 73% who would be classified as overweight. We have about 42% who would actually be classified as obese. It's a huge economic burden for the country, about $147 billion spent in 2008, and probably much more now. The obesity in general, of course, the problem is in part due to the weight bearing on our joints, and it's not great for our joints. But a lot of the complications that we don't want to have, for example, type 2 diabetes, the lipid metabolism disorders, cancer risks, fatty liver disease, all this is actually driven, or at least a lot of it is driven through inflammation. So what happens in obesity is that these complications arise because it drives low-grade chronic inflammation, which then leads to type 2 diabetes, atherosclerosis, and fatty liver disease. So one of the big problems is not really the weight bearing alone, but it's about the immune system. And that's where, as an immunologist from the University of Pennsylvania, I've been very interested about. So our initial goal was to treat the inflammation. And the way we wanted to go about doing this was to use a cytokine, which is an immune hormone, and it's called thymic stromal lymphopoietin, or TSLP. And an idea was to use this cytokine, TSLP, to treat the inflammation. And one of the reasons we wanted to do this was because TSLP, in our previous studies, we've shown that it has this remarkable effect on expanding these cells called regulatory T cells, or Treg cells. And these are a subset of T cells that suppress inflammation in autoimmunity and other inflammatory disorders. It is well known to be involved in allergic responses, for example, asthma. So there's a blocker that's used in treatment of severe asthma, but we were more interested in its immunoregulatory properties rather than the Th2 allergic response. Here's a data that we initially showed where we had a control mouse, or TSLP injected mouse, and you can see there's a big difference in the number of Treg cells in the systemic circulation, and in this case in the spleen. So the idea was, can we take TSLP, which would then lead to the increase in Treg cells, and then that would block obesity-induced inflammation. That is what we set out to do. So how did we test it? So we went to mice. So, regular mouse, if you buy it from Jackson or wherever, it's a lean mouse. This lean mouse, you feed it a high-fat diet for about 10 weeks and it becomes an obese mouse. So, and this is a great model for the type of mouse that we use. It actually developed, very prone to develop type 2 diabetes and fatty liver disease. So about 10 weeks, they're going to get some fat accumulation and they're going to develop insulin resistance. And the question we asked is that if we have a control versus TSLP for 4 weeks, what happens to these mice? And our prediction was that the diabetes would get better and also the fatty liver disease. And that's exactly what we found. So this is the data from the fatty liver disease. So this is the amount of triglycerides that are present in the liver of these mice. You can see that there's a lot of triglycerides in the control mice, but this markedly decreased almost to zero in the TSLP treated mice. On the same token, type 2 diabetes. So this is a measure, a HOMA-IR is just a measure of how much trouble you have controlling blood glucose. The higher the number, the worse you're off. So these are normal child mice. They control glucose well. If they're high-fat diet fed, they have problems. They have a higher number. And then if you have the TSLP treated mice, they go down. So the type 2 diabetes got much better. This was what we predicted. However, what was unpredicted was that TSLP had this major effect on obesity itself. So here is the weight curve of these mice. So for the first 10 weeks, you can see they're growing. They're almost double their weight over this 10-week period. It's all fat. We started the TSLP. They continue on a high-fat diet. So the control mice keep on gaining weight on the same trajectory. But as you can see, the TSLP injected mice, they suddenly reverse course. Despite being fed a high-fat diet, they lose almost back to their normal weight. So they lose all their fat in a period of 4 weeks. So when we initially saw this observation, I thought it was going to be something quite boring. I thought, man, it's a cytokine. They're probably feeling sick. They're not eating. So we went through this systematic approach of just figuring out what was going on. So we looked at the energy in and energy out. So there must be some imbalance, right? So if you're losing weight, there must be either less energy in or more energy out. So we looked at food consumption, and what we found, to our surprise, what they eat more. They eat about 20 to 30% more food. In terms of nutrient absorption, it was pretty similar. So energy in, if anything, was increased. So that doesn't explain why they lose weight. Well, how about energy out? So there's ways you can dispense energy. For example, you can burn fat by creating heat. You can have increased activity. You can excrete it through your feces or urine. And not showing the data, but there was no change in thermogenesis or basal metabolic rate. There's no increasing activity. Fecal excretion actually was down, so they actually poop less calories. And there was no change in the urine. So all this, which were on our list in terms of why the weight loss was happening, was all negative. So then we turned to this really unexpected kind of reason of why these mice might be losing weight. And it was all in their appearance. So here is a picture of mice. These are the obese mice. You can see they're quite plump. And after TSLP treatment, this is what they look like. They look like skinny, but greasy mice. And this is what all the skinny, greasy mice that lingo comes from, is that's what they look like. They're skinny and greasy. They look like they're wet, right? And they actually slip out of your hands if you try to hold them, because they're so slippery and slimy and greasy that they slip out your hands. So we wondered, what was this stuff on their fur? So we extracted the stuff from their fur, and sure enough, it's lipids. They're fats. So there's increased fats on the fur of these mice. And we wondered, is this something called sebum? So sebum is something that our skin produces naturally. But is it possible that the sebum is causing this weight loss, that they're spewing out so much lipids from their skin, and that was a reason? So how we tested that was, we took a mouse that could not produce sebum and asked the question, what happens to them if we give them TSLP? And in fact, they don't lose weight. So TSLP treated mice that cannot produce sebum will not lose weight. Of course, the normal mouse will. So, and then this is how we found out that, in fact, why these mice were losing weight was because they were spewing lipids out of their skin. So mechanistically, I'll just summarize what we found in a paper that was published in Science last year. And so what we found was TSLP, which is made by skin keratinocytes, can then stimulate T cells. So this is actually immunology. So it wasn't just metabolism. It actually did involve immune cells. It stimulates T cells. That induces a migration of these cells to the sebaceous gland. Here's the sebaceous gland that's attached to the pilosebaceous unit, or the hair follicle. And when you put this in overdrive by this mechanism, you get lots of sebum, but there has to be a source for all that lipid. And therefore, that source is body fat. So you get the extraction of blood lipids from body fat, which then end up in the sebaceous gland and end up on the skin. And this cycle then drives weight loss in these mice. So how do we then translate this to human, right? So that's kind of really the direction we want to go next. So Penn has partnered with a company, Abrax, and licensed out the sebum-inducing technology. So the idea is that we can take TSLP, or something that drives TSLP, to then allow for sebaceous glands to secrete sebum. And the way we're going to do it is through using not TSLP itself, at least for the very beginning, but to use MC903, this vitamin D3 analog that induces TSLP from skin keratinocytes. So you can see here in this schematic, you give MC903 to the skin. So it's a topical agent. It stimulates keratinocytes to produce TSLP, and that TSLP will then allow for sebum secretion and also increases Tregs. And that might be beneficial for a number of reasons. And in terms of the therapeutic implications, there are two things that we're thinking of. One is lipid related, of course, obesity, hyperlipidemia, type 2 diabetes, fatty liver disease, all of these are caused by obesity and increased fat. But also not only obesity, but also because sebum is a natural substance that our skin produces to protect our skin. And therefore, it could also be useful in skin barrier dysfunction. For example, dry skin, eczema, alopecia, dry eye. These are things that we could be targeting using this what we call an immune sebum axis. So with that, I'd like to end and acknowledge the people who were involved. Oops, something happened. Hold on. So I'd like to acknowledge there's tons of people, as you might imagine. It's a very multidisciplinary project. Couldn't be done by an immunologist alone like myself. The driver of the project, who did the experiment, was Ruth Cho. She's an MD PhD student, or was an MD PhD student at the time. She's moving on to MGH to do her residency in internal medicine. And then, of course, my lab members and a lot of other people that I don't have time going through. But this was a collaborative project that really ended up to be something cool, we think. So thank you very much for your attention.
Wow, thank you, Taku. I can
stop
see
sharing or
yes, I think.
Yeah, that's good, right? Okay.
Good. Yeah, perfect. So thanks. I think we already have a question from our audience. So why don't I start with that? Elisa Waxman asks, can the mice that do not produce sebum also experience the other positive effects of TSLP, or is the weight loss required for the other positive effects?
That's a good question. We actually haven't measured that. That's a really good question. We only really looked at the fat loss and the weight changes. I don't expect any of the regular T cells to be dependent on sebum production. We already know that involves dendritic cells. So if you specifically remove the ability of dendritic cells to respond to TSLP, we haven't published this yet, but we will be submitting for publication sometime soon. But those mice cannot respond to TSLP in terms of regulatory T cell expansion. And but they do produce sebum and they lose weight. So they're separate processes. They also get allergic response. So if some of pathologies can be driven by TSLP, and you get that even in the absence of sebum.
So I wanted to ask you to sort of go back and talk about how you sort of got interested in this sort of whole line of work, like working with TSLP in the first place? What led you to that?
Yeah, that's a great question. Initially, so TSLP is a cytokine that is produced by barrier surfaces. It's produced by skin keratinocytes, but also by lung epithelial cells and gut epithelial cells to some extent. And it's really what we call an alarmin. So it's produced at these surfaces where there's an interaction between the environment and the host, and it alerts the immune system that there's something wrong, that there's something coming, that it needs to prepare. So there's two parts to it. There's probably a homeostatic role that keeps things in check and maintain, but there's also a pathologic role when you drive it too much that you can actually activate immune cells. And so initially, the reason why we got into it was because we wanted to know in an allergic type of inflammatory response that is driven by TSLP, what happens to the regulatory component? And because there were at the time there was a report suggesting non-allergic inflammation, for example, those driven by type 1 responses, type 1 immune responses, would decrease regulatory T cells, that they would actually kind of get out of the picture so that they would allow for the immune system to fully develop or the immune response to fully develop. But type 2 responses are a little bit more tricky because they are driven by, for example, parasites that you would prefer to coexist with rather than actually kind of fight and die, kind of fight dying. You want to maintain a balance and coexist with a parasite because it would be very difficult for the immune system to get rid of it. And in those cases, we thought that maybe under those type of inflammatory responses, regulatory T cells would actually increase or maybe maintained because you don't want an overt inflammatory response. And that's why we use TSLP. We didn't really think it would have that much of an effect on the Tregs, but it did. And we got interested because we thought, oh, wow, maybe we have a way to expand regulatory T cells and control inflammation. And at the time I studied regulatory T cells, and that's why we were very excited about that finding.
Interesting. So when you saw the observation about, so TSLP is an anti-inflammatory. So why, when you saw that it was acting on the sebaceous glands or through the T cells, what was that surprising? I mean, why would this anti-inflammatory be working on having an effect on the sebaceous glands?
Right. I think there's two questions, I guess. One is it surprising that TSLP could control the sebum? I think that actually is not as surprising. I mean, of course, it's surprising because we never knew at the time. But now that we found out that it does, and we think about it teleologically, then perhaps it's not as surprising because TSLP is a barrier function cytokine. It responds to environment. And, like, for example, the skin, if you have some kind of insult at the skin and it triggers TSLP release, you would want to have enhanced barrier function. Right, it's kind of because sebum of the skin is analogous to mucus of the lungs or mucus of the gut, right? So when we have an infection in our lungs of COVID, whatever it is, we produce a lot of sputum, we produce mucus, right? And that is a protective mechanism that our barrier surfaces have. So it makes a lot of sense that the skin has a similar function, right? So that if there's an insult that drives TSLP expression, that would in turn drive and increase the skin barrier function. And that could be through sebum. And sebum contains a lot of antimicrobial peptides in it. So it does actually have a direct effect in regulating the commensals and other bacteria that might be on our skin, which of course we always have. The second question you asked was, what was T cells? That was very surprising to us. Because if you think about skin barrier function, that's very primitive, right? It's such a primitive mechanism, so it's really a kind of physical blockade of preventing things from coming in through our skin. And T cells, which we kind of think they're more sophisticated than something like that is more specific. If you get infected with a virus, they're very specific to that virus. If you're to a bacteria, they're very specific to that bacteria. It's an adaptive immune cell. So the adaptive immune system controlling sebum was quite surprising to us. And that is really something that we're investigating further in terms of why does it have to be T cells? Why, what's the relevance of T cells in this whole phenomenon?
Do going back to the slides you showed, did you give, so you start the TSLP and then over 4 weeks, the mice lost all that weight, almost all the weight they'd gained. Do you have to give TSLP continuously through that period, or was it just dosed? How was it? Explain the dosing of that.
Yeah, so in our case, so we did it by two ways. One was to use TSLP directly, not in the form of a cytokine because it's quite expensive, but we force expressed it by genetic methods. So one was by using a virus that would force express TSLP in the liver. So it's coming from the liver. We also used injected cells that would produce TSLP in the skin. So there would be just kind of factories of producing TSLP. So we did it in two ways. We also used the drug MC903, which we can put on the skin, and that would induce endogenous TSLP production from skin keratinocytes. And in all ways, it does work. In terms of whether or not TSLP is required continuously, we don't know for sure if that is the case. But we do know that T cells are required at all times. So, so one experiment that we did was we injected TSLP. So the mice are continuously producing TSLP and they're losing weight. We can acutely get rid of T cells at that time. So the T cells will be removed. And what happens to those mice is that if the T cells get removed, then they revert. So, they're losing, losing, you deplete them, then they bounce back and now they become normal actually. So we do know that a continuing presence of T cells is required. But to answer your question, your initial question, we don't know if TSLP is continuously required yet. We just haven't had a way to do that well right now, but eventually we will. So that's a great question.
Yeah. So obviously we're talking about mice here. What are the, as you think about moving these findings into people, and I think your first target, you said, there's both obesity and obesity-related diseases, but also skin diseases. What is your focus? Your plan is to start with skin diseases? Is that because that's sort of an easier target, or what's your thinking about that?
I think so. The reason why we're kind of going in baby steps is that the effect that we see with TSLP on the mice is too dramatic. You don't really want to lose all your body fat in 3 weeks. I don't know what's gonna happen. You'll have to probably take 10 showers a day. But beyond that, I think it might be dangerous as well. So what we're trying to, because there's two things that we can go after. One is the skin disorders, which probably would take less sebum production to still have an effect, that we could do a dose escalation study to kind of see where that happy medium is, right? So if we're dosing it up, we expect to see some skin protection early on, and then even at low doses. But then if we start to increase that and we get more and more sebum production, we hope to see extraction of lipids from the circulation. So probably the initial thing we would want to see is, what happens to triglycerides, for example, in circulation of these patients. It may take, maybe a few months for them to lose, some kind of weight. Because you can, of course, compensate by eating more. So, right, so it does have to be balanced. But, to what extent can we then change the lipids first in the blood? And then eventually, because of those changes in lipids, do we see an effect on actually weight loss? So we're kind of going in baby steps.
Right. So you mentioned there that, there's of course been lots of people trying to come up with weight loss treatments, and most of them haven't worked well. If they do, they seem to have a very short-term effect. People they'll lose weight and then bounce back up. And you alluded to that in your answer in the last question, that, people often will start eating more, or their some other metabolism shifts. Do you have any sense of whether, I mean, first of all, how long did you follow these mice? Just the 4 weeks, or do you know what happened to these mice after 4 weeks, or do you have any sense of whether this would be any different from all the other failed obesity treatments?
Yeah, I mean, I think that's a tough question to answer. I don't know, of course, if there can be compensation. The mice can't compensate because they will actually lose every single fat. I mean, you can't find any fat in these mice after 4 weeks. It's really hard to find it. And eventually, because they lose so much fat and they can't keep up by eating, so they actually become hypothermic. So they can't maintain the body heat. Because they're wasting so much lipids from their skin. Of course, we don't want to see that in humans, but given that at face value, you could say that even if you increase your food intake, you may not be able to completely compensate. Maybe part of that has to do with the biology that we have. It's really specific to lipids. So if you look at other weight loss regimens, I think you would lose muscle and other tissues as well. So other sources of energy. And in fact, you might even lose muscle first. But in our case, actually, in our mice that we've tested, there is absolutely no difference in muscle weight. They don't lose any muscle. They only lose lipids. And that is probably because sebum is mainly lipids. And they probably can take, so some of it is probably glucose. They can make lipids from glucose by lipogenesis, but they can also take directly free fatty acids and triglycerides from the circulation to replenish that wastage that's happening at the skin. So even with the weight loss, it's quite interesting because when you look at, so in the high fat diet, it's easy to see the weight loss because they're so fat. So if you go to, if you're 45 grams and, half of it is fat, then if they lose their fat, you're going to lose a lot of weight. But in a lean mouse, right, that's 25 grams, 27 grams, their total fat mass is like 2 grams or something like that, in that range. So if you give it to a lean mouse, they still lose all their fat, but the delta is quite small in terms of total weight because they actually don't lose their muscle. They only lose a little bit. So it's actually quite hard to notice. Even if you measure, it's like, oh, it's like a 1 gram loss, 2 gram loss in weight. So you're like, okay, did they really lose their fat? You open them up and then you're like, oh yeah, it's gone. So the fat's gone, yeah. but the muscle's still there. So it's in that sense, it's quite attractive, I think.
Yeah. Is the biology involving, that was involved in the mice, is it similar in humans? Are they a good model for humans in this case?
That's a $100 million question. That's that's really the question we're trying to answer in the clinical trials. Is it the same? I'm hoping that at least I think these things, like these primitive things like barrier function, there must be some preservation among species. Because really the purpose of this axis that we discovered is not to control weight. There's in any way I'm not proposing that humans or any other animal controls their weight or lipid metabolism by increasing or decreasing sebum production. Right. The reason why they increase or decrease their sebum production is because they're responding to an environmental stimuli. That is what I think, or a central thing, right? So like hormones could control how much sebum we produce depending on our age or sex. So that is the reason why we produce sebum, but not because we control weight. It's just that, when you put it in high gear, like we've done with TSLP, because it is very high calorie, that you can actually use it or take advantage of this mechanism. But because the mechanism is so primitive, I am predicting that if not exactly the same mechanism in mice, that there must be a similar mechanism that is operational in humans. So hopefully we'll get more data from the human studies and figure out what that is. If it's slightly different, we'll hopefully figure that out.
Yeah. Just a reminder to our audience to please, if you have questions, and we'd love to hear from you, please type them into the Q&A function at the bottom of your screen. So when I looked at the photos of the greasy mice, I thought, well, gee, it's great that they lost weight, but now they're like all greasy. So how do you, presumably that's not a good side effect of any treatment. So how would you control for that? Should this work in humans?
Well, I would have to take the word of the judge that was at the Stat Summit saying that this is great, right? On the other hand, because now not only am I losing fat, I have an excuse to take another bath today, right? So for some people, it might be positive, right? They're like, okay, I can take another bath. I can spend another hour, in a warm bathtub. But yeah, you're right. I mean, for most people, it might not be that, favorable to have too much lipid on your skin. And I think that's why it needs to be controlled in baby steps, right? So it's not like, those greasy mice, of course, I mean, they lost all their fat in 3.5, 4 weeks. And that's not what we're trying to achieve. We're not trying to achieve, 100-pound fat loss through the skin in 3 weeks, right? That would be a problem. I don't know what's going to happen to the skin when that happens. But so that's why I think it's important to kind of take it in smaller steps. And because I think if for example, the amount of calories we secrete through our skin per day in the form of sebum is about 140 to 150 calories per day. So if we can increase it to, let's say, triple, right? So 2 times more oil on or 3 times more oil on our skin, that's 300 calories per day. And that's not bad, right? That's, an extra sandwich, a little bit less than a burger a day that you would be wasting through your skin. And, but if you do that, continuously, because it doesn't stop, that, eventually, if you keep your food intake constant and you do the math, you would be probably losing about 1 pound of pure fat per week. Right. And that's different, right? Because mainly when people do have weight loss regimens, it's a lot of water that they lose initially. And then there's muscle and then eventually fat. But it takes a while for that fat to go away.
Yeah.
And I think in our case, being that it's, at least in mice, we don't know in humans, of course, but at least in mice, it's really specific to lipids and fat that, even though you may not be losing weight in terms of weight, you're losing a lot of fat, right? And in doing so, really, going back to, of course, there's, people want to lose weight because you might look better or you feel better or whatever it is, but it's, it's not that, right? It's really the reason that we're doing this is because of the complications that are resulting from obesity. It's not, how you look, right? Really, it's about, diabetes, it's about fatty liver disease, it's about all these other things that's really a trouble. And by losing those lipids and hopefully at the same time decreasing that inflammation with our approach, we could really start targeting not obesity all alone and lipids alone, but obesity related inflammation as well, right? So in that regard, we're quite excited about this whole axis in terms of kind of putting it back to normal.
Right. So we have a question from Meredith Mann. She asks, would increasing sebum production contribute to increased acne and other skin issues?
Yes. So that definitely is another problem, right? That needs to be controlled. And that's why it's going to be, we have to see it in human. So in mice, we really can't test that because the C. acnes, which is the bug that causes acne, does not grow well on mouse fur or mouse skin. So it's quite tough to test that to see if it's better. It actually would probably be dependent on the composition of the sebum that we really haven't gone into yet. So it's possible that TSLP could change not only the amount of sebum that's being released or produced, but the composition as well. Is it more heavy in free fatty acids? Is it more heavy in triglycerides or more, cholesterol esters? What is actually on the skin, especially of humans? And that could be great studies to do in the clinical trials, right? Once we see an increase in sebum, is the composition of the sebum different? And if so, it has been shown in many studies that the composition of sebum really could dictate whether or not acne, C. acnes would grow. So, for adolescents, I think it might be, problematic, but, I don't think our drug is really targeted towards adolescents. I think it's like for people like me or my age, so, people who have drier skin and, have less sebum production at, at baseline. I think those are the people, not people who are, oily and greasy, in their adolescence and they're taking 3 showers a day regardless. So I think, but that's a great question. So we definitely have to look out for the development of other skin diseases that are related to sebum.
Yeah, but you are looking at TSLP and this approach as a treatment for various skin diseases. I think your first trial that you hope to start as soon as next year is in atopic dermatitis. Can you talk about why you chose atopic dermatitis and how you hope that this will work in that disease?
Yeah, so we were hoping that, so we're thinking about skin barrier dysfunction. So some of the diseases that you would think of that, starts, at least not in every patient, but on a lot of patients, you do see a problem in skin barrier function. And that can lead to inflammation because the skin is more easily penetratable by bugs. And eventually that the disruption of the barrier can lead to the atopic march, which then can lead to other allergic diseases like asthma and other allergies. So it's kind of the start is the disruption in skin barrier function that could be caused by a number of reasons. It could be genetic, it could be the environment. But what we're hoping to do is to correct that skin barrier function. Once it gets to a severe state of atopic dermatitis, I'm not really, and that's not our target really. I think you would need a stronger anti-inflammatory to really quell the inflammation. At that state, you're really not be able to cure it just by, protecting the barrier surface. But in early stages, right, especially, if somebody's just using a cream or some ointments or some steroids just to kind of get, the mild to moderate dermatitis better, at that stage, I think it's actually going to be quite beneficial because emollients, are good. As long as they stay on the skin, right? But, if you have, for example, your hands are, dry and they're cracked and you put cream on your hands to protect them, well, you're going to wash your hands, right? Many times during a day, especially with, in the area of COVID, right? People are washing and putting alcohols and putting all this bad stuff on their skin anyway. And that's where I think our type of therapy, it would be beneficial because you're really curing the disease from the inside out, right? So the sebum, because, it's kind of, emollients are outside in, right? So you're putting creams to moisturize the inside, whereas for us, it's coming from the inside, right? So the sebum production from the inside and protecting the outside. So many times wanted why we went after atopic dermatitis. We are going after other. Am I breaking up here?
You broke up just a little bit there, yeah. So, but you're back.
I'm back. Okay, great. So in addition to sebum, there is another very similar substance called sebum, and that is an oil that we produce in our eyelids. So our eyelids have these glands called meibomian glands that are quite similar to sebaceous glands. And we have data to suggest that those meibomian glands are also increased in function by the same mechanism. And what that means is that, so the reason why we make oil in our eye is for our tears not to dry so quickly. So dry eyes is kind of, again, barrier function, right? It's protecting our eyes, right, from drying out. So the tears don't dry out very quickly. So if you have dysfunction of meibomian glands, you could actually, potentially correct it in, for example, in dry eye, like Sjogren's syndrome, for example. And so we're looking at these barrier function type of things initially, right? But then, we're going to gain data and really do a dose escalation study to figure out where can we be to actually have an impact on circulating lipids and then, of course, obesity eventually.
Right. Interesting. So we have a question from Kate Dumont. She asks, is TSLP naturally occurring in plants?
I don't know that. I don't think so. I don't think so. But I can't say 100%. But I would think that it's not. It's a mammalian thing. I think sebaceous glands are also mammalian as well. But that doesn't mean, of course, TSLP has other things to can do other things. But because plants don't really have an immune system, I really don't know if TSLP is produced. There are forms of TSLP that actually have direct antibacterial function as well. Actually, TSLP does too. So, I mean, if it's produced, it probably serves an antibacterial role. But I don't know for certain.
Does in the mice, when the experiments you do with the mice, so other than, of course, the concern, the greasiness, were there other responses you saw or side effects that you have to sort of think about as you try to translate this to humans?
Yes, there are. But that could be. It really depends on what's the biology in humans, and that will really determine how worried we should be about those different axes. So as I introduced at the very beginning, TSLP is well known to drive allergic responses. There's an antibody actually targeted, a blocking antibody targeted to TSLP that has been approved for the treatment of eosinophilic esophagitis or severe asthma. So, it actually is important in driving inflammatory responses as well, right? So you might think that, well, that's kind of the opposite, right? Yeah. So it's really a balance though, right? So TSLP, not only can drive this allergic response, but it can also have this immunoregulatory kind of barrier function effect as well. So it's really, a balance of those two processes. So in mice, when we see, these mice don't develop per se when we overexpress TSLP, asthma or anything that we can see, but there is some degree of inflammatory cells that we see in other organs. The question is, well, so there's also a dose responsiveness, right? So that's why we have to be careful in terms of how much TSLP is going to be produced, because at lower doses or more homeostatic doses, they might serve much more a role, towards, homeostatic function like skin barrier function. But, when it's really high, then it could drive more pathologic immune responses, right? So I think that needs to be worked out. Another thing that kind of throws a wrench in the whole thing when we translate to humans is that in humans only, and that's why it's so hard to test, only in humans and potentially chimpanzees and bonobos. So those are the only 3 species. And those 3 species, including us, of course, is that they have 2 isoforms of TSLP. So one is what we call long form TSLP, and the other one is called short form TSLP. Long form TSLP is just like any other TSLP in any other species. That's the TSLP that people talk about. It's long form. But there's a short form TSLP that's expressed only in humans and, again, chimps and bonobos. And that is a truncated version of the long form TSLP. People don't know exactly what it does. It's quite recently described. There are only a handful of manuscripts that describe what it does. But it seems to play a homeostatic role, much more of a homeostatic role in regulating immune responses. So it's more anti-inflammatory in nature, and it has more antibacterial activity. So it seems to be much more of a barrier type of cytokine than the long-form TSLP is. And it's possible that humans have evolved to kind of separate those two functions, right? So in mice, it might be that it's really the amount of TSLP that dictates whether or not you have a pathologic response or more homeostatic response. But in humans, it might be that there's a division of labor, that you have long-form TSLP for more of the pathologic allergic responses, but the short-form TSLP, which could actually handles the more homeostatic things. And if that's the case, and then by kind of harnessing that angle, that short form TSLP rather than long form, we might be able to mitigate a lot of the side effects that we might expect in other species and really hone in on the mechanism that we want, which is a lipid lowering and the increased barrier function.
So are you working on experiments now with the short form TSLP?
We are. So part of my lab is looking at the expression. The hard part is that we have to use human samples because it's not expressed in any other species. That's why it's so difficult to really get at the heart of it, because just using samples and doing correlative studies, it's kind of hard to tell, is it is a chicken egg, is what is the relationship between, is there cause effect relationship? But initially we're just doing just correlative studies in human. We're also using human cells to see the responsiveness to short form TSLP and how they might differ compared to long form TSLP. But we're definitely performing those studies.
Yeah. Just want to let the audience know we have only a few minutes left. So if you have questions, we'd welcome them and welcome you to be part of the discussion. Please type them in the Q&A box. Thank you. So where are you going from here with with the work? We've talked about the atopic dermatitis, but what's your path, do you think, and how soon, if things work out, how quickly might you get to clinical trials for some of the more systemic, the obesity and other systemic effects of the
So in terms of direction, so there's two things. Well, one is more the clinical translational aspect, which the first studies, we're doing some phase 1 studies, endpoints not being primary endpoints being safety and tolerability, of course, but really getting some surrogate measurements of seeing how much of an impact do we actually have with elevating TSLP, and how that then relates to either barrier function or of course lipids and regulatory T cells, all those things that we found in mice. And that's one thing. I mean, I think we're trying to aim for kind of the dry skin eczema type things in next year, and maybe a year after that we can start with the more the lipid related disorders. So maybe a couple of years for the lipid disorders. So a year delay. That's once we get more data in human. In terms of the basic science, I think what's very exciting, I think, again, is the T cells. Like, why are the T cells involved in this process? So we're going to figure out, what is it about these T cells? What's special about them? Is this a T cell kind of subset that maybe is really important for barrier function? Like, have we identified a new T cells subset that is important in you're kind of controlling barrier function, not only in skin, but maybe in the lung and the gut as well, right? So it could be that there's certain transcription factors that drive a program in these T cells that then induce, changes in mucus production, changes in sebum production, or even other more innate type things that really protect us for our barrier. So, so we're doing, transcriptional analysis, single cell transcriptional analysis of T cell subsets in the skin and in TSLP treated mice and all that, to really figure out what could, some of the drivers be mechanistically in having this response, and how global it could be. Is it just a skin related thing, or is this something that's kind of applicable to all barrier surfaces? Another thing is, kind of going back to the environment, like what are the environmental triggers, and how does, the commensals and other things that are on our skin and if it's applicable to the gut and the lung too, like how are these interactions taking place in, what is the role of this axis that we identified in those processes? So those are kind of the exciting, I think, new areas in terms of the basic science that we're heading to. And I love it that there's also a translational component in terms of therapy. But I think there's two really exciting areas that both basic and translational that we can head to in the next few years.
So just as a last question, I imagine that you never thought you would, when you started out on this route of research, that you would be working on a potential obesity treatment. And so what does that tell you about the way science works? And
yeah, I mean, I think that's a great question. So my motto is to really kind of have the data lead you. We're not the hypothesis, your original hypothesis. Of course, as scientists, we always know that most of the time we're wrong. Our hypotheses are wrong initially going in, and you keep on refining those hypotheses based on what the new data are. And I think that's exactly what we found here, is that we just let the data lead us where we had to go. It could have been that was metabolism and not sebum. I mean, we never thought we would, do sebum. I mean, that was our initial, inkling, was that it's going to increase the metabolism in these mice, but it didn't, right? So we had to really do, and a lot of credit to Ruth Cho, who's the first author on the paper. She did an immense amount of work, really digging in deep and trying to figure out what was actually wrong about these mice. Not really wrong, but what's different about these mice that made them lose the weight. Another thing that it really highlights is the way that science is going in terms of collaboration, and I think people have mentioned this a lot of times, that nowadays it's not it's not a one person thing. You can't have one lab do everything. In order to make discoveries that are innovative, I think you need to involve a lot of people and involve a lot of different areas of expertise to come together. And I think when you do that, you do get actually some paradigm shifts, rather than incremental advances. And I think it really highlights the collaborative aspect of science, especially nowadays. I'm great and really grateful that Penn is a very collaborative place and people are willing to help, and tons of collaborators, and it's been a lot of fun.
Well, thanks, Taku. We're out of time. I want to thank you for joining us today. I want to congratulate you again on your
Thank you. That was fun.
Your win, your double win. Thanks to the audience for your questions, and I also want to thank our event sponsor, Novartis, for hosting this event. Please be sure to check out STAT's next big hybrid event, our 2022 Health Tech Summit, which will be taking place both virtually and in person in San Francisco on May 24th. More information about the program and how to register can be found on our website, statnews.com. So thank you again. Stay safe and be well.
Thank you, everyone.